So right now we have defined how to compute the distributed losses. The following step will be to define how to compute the concentrated losses, but before moving to the following step, let's sum what we have seen right now. So basically, we have started saying that along the movement of your flow, it encounters some problems. So basically, along the motion of your flow, you see that there are some distributed losses. These losses are quantifiable through the shear stresses tau 0, which is given by gamma times R times J. So the aim becomes to compute this J, which again is called the hydraulic gradient. Alright, J is also defined, as we have seen in the beginning, that is equal to the total head in the first section minus the total head in the second one over the distance between the two sections where you're evaluating this gradient. Alright, but it's not so easy to compute because we have seen that J depends on different parameters. In particular, you can have a formula that is called the Darcy-Weisbach, and this formula says that J, your hydraulic gradient, is equal to lambda over the diameter of the pipe times V to the power of 2 over 2G. So the problem is not to compute J anymore, but is from J to compute lambda. Who is lambda? We have defined lambda as the friction factor. This friction factor depends on the regime of flow that you are considering. So, for example, in laminar flow, we have demonstrated that lambda is equal to 64 over Reynolds. Then we have the case of, it was the transition, the transition flow. So the case in general smooth pipe, so both for transition, both for turbulent flow, so it was transition flow, turbulent flow, but smooth pipes. We can say that it's valid Prandtl von Karman, which says that 1 over square lambda is equal to minus 2 the logarithm of 2.51 over Reynolds times square lambda. So we want to compute lambda. We have three cases: laminar, transition, turbulent flow in smooth pipes. Third case is turbulent flow, but in rough pipes. So again, there's another Prandtl von Karman law that says that is 1 over square lambda is equal to minus 2 the logarithm of 1 point over 3.71 times A epsilon over D. Everything can be summed in two different things, which are, on one side, Moody diagram, and on the other side, which again it reparted the three regimes of flow, and it makes you see that graphically the dependence of the friction factor on the different parameters, plus Colebrook-White law, which says that 1 over square lambda is equal to minus 2 the logarithm of 2.51 over Reynolds times lambda, square lambda, plus 1 over 3.71 times epsilon over d. So this stuff, or this stuff, say exactly the same thing. Alright, we have also seen, just to sum everything, so this is true, and we put it right here. We have also seen that there are some practical water mains formula, which says that basically if you are in the condition of turbulent flow, so remember that Darcy-Weisbach is a law that is valid for every kind of flow. But in particular, if you are in front of turbulent flow, you can say that J, your hydraulic gradient, is equal to V to the power of 2 over K to the power of 2 times the hydraulic radius. Remember that for a circular pipe, the hydraulic radius is equal to D over 4. Then, let's try to again recall Chassis. So this is Chassis law. And remember that from Gaukler, it's Gaukler, Strickler, you have that K is equal to Ks R to the power of 1 over 6. So substituting these things inside this law, we get, in the case of turbulent flow, that J is equal to V to the power of 2 over Ks to the power of 2 times R to the power of 2 over 6, which became 1 over 3 times R. So it's V to the power of 2 over Ks to the power of 2 times R to the power of 4 over 3. Remember that we are in permanent motion conditions, so we have that the volumetric discharge Q is equal to V times A. So we can insert these things right here, and we get that J is equal to Q to the power of 2 over Ks to the power of 2 times R to the power of 4 over 3 times A to the power of 2. Remember that Also, r again is equal to d over 4. So we can also express this stuff in this way. It's q over to the power of 2 over ks to the power of 2 times d over 4 to the power of 4 over 3 times, let's try to move everything because I don't have no more space. I hope it's visible. Let's see. Yeah, it looks like so. So it's pi d to the power of 2 over 4, which is the cross-section area to the power of 2. This becomes 16, which is 4 to the power of 2 right there, bring it in the numerator, times 4 to the power of 4 over 3. Alright, and this is 1 and 2. Then we have pi to the power of 2 that remains in this denominator, that multiplies q2 over ks to the power of 2 times d to the power of 4 over 3 times d to the power of 4. So if you make this computation right there, you get 10.29 q to the power of 2 over ks to the power of 2. Then we have this stuff, which is 3 times 4, it brings you, so it's 4 over 3 plus 4, which means 3, 4 plus 12, so it would be 16 over 3, and 16 over 3, if you make the computation, turns you out the value of 5.33, so it becomes d to the power of 5.33, which is exactly 16 over 3. Hence, this allows you to completely evaluate completely directly the Q. Of course, we said that to evaluate the verification problem, which means to evaluate the volumetric discharge inside your systems, you should have some information about the regime of the flow, so you must know the Reynolds number, because if you know the kind of flow, you know if you are in the case that you can consider, for example, only Chazy law, or if you are in the case where you have to consider Darcy-Weisbach, so the generical formula. So, first thing is to make an assumption about Reynolds number. You do this, you evaluate the friction factor, or if you make the assumption, for example, that you are in turbulent flow, you can evaluate directly Chazy, just knowing the roughness of your pipe. Then you compute J. If you compute J, you can evaluate the losses, and exactly you can evaluate your Q. You compute the volumetric discharge, and when you have reached the Q inside the system, you can re-evaluate Reynolds number and see if the two values from one step to another one are the same or are different. Alright? So, let's go back to our presentation and let's see what happens if we want to compute the concentrated losses. Okay, so basically for concentrated losses we are considering again permanent motion, which means that your volumetric discharge is independent from space and time. And what are basically these concentrated losses? These concentrated energy losses are something related to a kind of different variation of the geometry inside your pipe. So, usually pressurized flows move inside circular pipes, except particular cases when you can encounter junction among trunks. When you have this variation of the geometry inside your pipe, then there can occur some intensive energy dissipations, and these dissipations are caused by the separation of the fluid stream from the wall. So consequently, there are the formations of some kind of vortices. Concentrated energy losses are estimated through these formulas, which means that the difference of total head before and after your point where you can see the concentrated energy losses is given by a factor times something depending only from the velocity of your fluid. The most important case when you consider the concentrated energy losses is, of course, the sudden enlargement. So let's try before to see it right here and then to demonstrate this thing. You can find this also in the materials that has been scanned and uploaded on the website. So basically, what is a sudden enlargement? Suppose your flow is moving inside a pipe characterized by cross-section A1. Then, at the point, the diameter of your pipe increases, and what happens? It happens that your flow is still moving, so you're in permanent motion, and it means that the volumetric discharge here is exactly equal to what you see right here, so the Q is constant. But if the Q is constant, and so if it's valid the continuity equation, you can say that, for example, moving from A1 to A2, so increasing the diameter of your circular pipe, hence increasing the area of your pipe, if Q have to remain constant, the velocity from this point to this one, of course, will decrease. So in A1 you will see a velocity which is really much higher than the one that you will see in A2. To study the sudden enlargement, which is one of the first concentrated energy losses that we will see together, suppose that, for example, you want to define some assumptions. First, we have to define some assumptions, and these assumptions are that the density of the fluid is constant, you are in front of a linear flow, which again it means that you are considering on each section an hydrostatic pressure distribution, there are no shear stresses relevant, and also you are considering turbulent flow. So basically, according to Coriolis coefficient, it means that this coefficient is equal to 1. First things that we will say is that moving from section 1 to section 2, we would apply what? Bernoulli theorem from this point to this one. Bernoulli, of course, extended to a flow. Then, the other equation that will help us to solve this kind of problem would be, of course, the momentum equation. And the momentum equation is something that comes from the equilibrium of the momentum equation. So basically it's the first thing that we will see is to isolate the control volume inside your system, and then once we have isolated this control volume, compute all the force of all the system force, and to evaluate when these force are the effects of this force are equal to 0. Comparing these two things, somehow we will get this expression, which means that delta H, which is again the difference between the total head in section number 1 with the total head in section number 2, is something depending only on the difference of your velocity, and consequently is something related to k, which is this factor to the power of this is k, of course, times v2, so the velocity in the larger section, to the power of 2 over 2g. So let's try to solve these things together. So again, let's take our paper. And let's try to move it to make you see what I'm going to write. Alright, so again, we want to demonstrate this sudden enlargement. So, recalling the scheme that we have seen on the paper, we have a pipe, an enlargement, this part is characterized by A1, this part for A2. We have seen that moving from this stuff, from this point to this one, the total energy associated with the fluid decreases. Decreases because you have this variation of the geometry inside your pipe, which creates lots of turbulence right here, and this turbulence dissipates the energy of part of the energy of your fluid. So basically you are first a value of total energy, which is H1, and then you will have, in proximity of this enlargement, a total head equal to H2. Of course, since the piezometric gradient H is total head minus v to the power of 2 over 2g, we can say that in this case we have then, which is H1, and the difference between these two lines is exactly v1 to the power of 2 over 2g, while right here your velocity decreases, so also these things right here decreases, and is v2 to the power of 2 over 2g, and this line is H2. Alright, so let's try to compute this thing. So basically, first we have to consider what is our control volume, and for example I can choose, a moment please. Okay. I can choose, for example, to take the section before and a section after our sudden enlargement. But the control volume is something like this, because the control volume must be something where you can consider still valid the assumption to study the problem, so your fluid must be linear. And in this part, of course, not, because you have turbulences. So basically, this is your control volume. Once you have defined the control volume, we can just first study Bernoulli from this section to this section. And to do this, we can say that, for example, the total head in section number 1 minus this stuff, which is delta H, because it's the decreasing due to the concentrated energy loss, is equal to the total head in section number 2. So H1 is exactly Z1 plus P1 over gamma plus V1 to the power of 2 over 2G minus delta H, and everything is equal to Z2 plus P2 over gamma plus V2 to the power of 2 over 2G. Alright, so we isolate delta H from this one. We get that delta H is equal to, assuming that we are moving, for example, in the axis of, so it means that Z equal to 0. Alright, so if that is equal to 0, we can get that Z1 is equal to Z2, so Z1 is equal to Z2, and we get that delta H is P1 minus P2 over gamma plus V1 to the power of 2 minus V2 to the power of 2 over 2G. Problem. P1 minus P2, sorry. So we want to define this difference of pressure between this section right here and this one. Remember that if we have taken z equal to 0 on the axis, it means that P1 over gamma is exactly this stuff, while P2 over gamma is exactly this stuff right here. Hence, we want to define P1 minus P2. Because once we have defined this, maybe we are able also to compute delta H. Alright, so to do this, so first we have applied Bernoulli's theorem between section number 1 and section number 2. But to compute this difference of pressure, we want to create the system related to the dynamic force. So, again, Let's take another paper. And let's try again to take our system to make the system force. So here is your control volume again, and it was from this one to this one, but also considering that there's this part. Let's see what are the system of force that act on your control volume. So if this is control volume section number 1 and section number 2, we will have to consider different kind of forces. In particular, we will have the weight of your control volume, then we will have the momentum of the related to the link, related to the flow, so to the velocity of your fluid, which is called Q1 in entrance and Q2 in the exit. Sorry, this is of course rectilinear. Then, acting on your control volume, you have forces that depends on the pressure. So again, we are assuming that we are considering an hydrostatic pressure, so linear flow, which means that right here we have in the barycenter of our cross section number 1, we have pi 1, while right there we have pi 2, where pi are forces that comes from the pressure on your section, so they are hydrostatic pressure forces. Applying in this way the dynamic force on control volume, we say that S, which is the force that the fluid gives to your structure, is equal to G plus pi 1 plus pi 2 plus pi cc, which is the pressure related to this part, which is not your control volume again, plus what is entering, Q1, minus what is going outside, Q1 and Q2. Alright, so this comes from another dynamic equation which says that the system of all your forces acting on your control volume is equal to 0. So basically, there's a preliminarily we would have said that G plus pi 0, where pi 0 is the force that the structure gives to your fluid, plus P1 plus P2, pi 2 plus pi c